Good morning, my name is John Dominguez and I'm an applications engineer here at Mori Microwave. Today I will be talking about the most common passive impedance techniques, focusing on the challenges for FR1 and FR2 bands. The presentation will be divided into the following sections: motivation for impedance tuning, introduction to passive tuning, important considerations, state-of-the-art solution for FR1 and FR2 frequencies, a live demo, summary and conclusions, followed by a Q&A.
Why load pool? Load pool is the act of changing impedance to a DUT. PAs, LNAs, transceivers, or a simple transistor are examples of typical DUTs. S parameters are able to only predict the linear response of a DUT, but doesn't allow an understanding of the behavior at large signal. Transistors show nonlinear characteristics in large signal, creating harmonic generation and frequency mixing. Load pool measurements allows us to understand, model these behaviors, design PAs, and test the ruggedness of the final design. In the industry, we also talk about source pool, which is the act of changing the source impedance at the input of the DUT to properly model and validate the noise figure behavior under different source conditions. In this presentation, we will mostly focus on the load pool using passive tuners. Applications where load pool is used range from transistor characterization to model validation and extraction, as well as matching network designs for PAs. These are typically on non-50 ohm DUTs and can be on wafer or fixture. At system level, 50 ohm DUTs, load pool is used for design validation testing, typically known as DVT, and reliability, where we validate the DUT is still functioning for high mismatches. As mentioned, load pool is the act of presenting a set of controlled impedances to a DUT, and then measuring a set of parameters at each impedance point. The simplest approach for tuning is using a passive tuner. Tuners use a mechanical component called a tuner, where a probe, seen here in yellow in the figure, is inserted in an airline, seen in green, to create a reflection. The magnitude and phase of the load impedance are then adjusted by varying the position of the probe or slug in both the X and Y axis along a 50 ohm airline, as shown in the figure. By moving the probe up and down, left and right, it's possible to present nearly any impedance to the DUT, as long as a magnitude of A2 can remain sufficiently large so that it can be achieved. It's important to note that gamma load is less than 1, since A2 will always be smaller due to the losses between the output of the DUT and the tuner. Some key points to consider are: it's simple to set up, easy to integrate in custom code. Gamma limitations: due to the distance between the tuner probe and the DUT, coupler, cables, etc., the gamma will be limited. This limitation becomes critical at high frequency. Speed: the tuning is based on mechanical motion. We will always be limited by their speed. Phase skew: this is particularly relevant for modulated signal, where an impedance needs to be set over the frequency bandwidth of the signal. Due to cables, couplers, probes, for example, the phase of the reflection will change over frequency. I will cover this topic with more details later in the PowerPoint. As mentioned in the motivation slide, transistors show nonlinear characteristics in large signal, creating harmonic generation and frequency mixing. Optimizing the harmonic termination enables waveform engineering, boosting device performance like efficiency. To properly apply, the impedances need to be controlled simultaneously for all harmonics, where high gamma across 360 degrees are desired at the second and third harmonics. There are two approaches to doing this using tuners. One method is using single tuners in a multiplexer mode. This means a triplexer will split and then merge the signal from the DUT to the tuning probe. Each tuner will control one harmonic. The advantage of this approach is the isolation between the impedance is as high as the isolation of the triplexer. The disadvantage is that it's not a user-friendly solution for wideband tuning, where multiple triplexers need to be used. Another issue is the insertion loss of the triplexer will affect the tuning range. The second method is cascading the tuners. This approach can use 2 to 3 tuners cascaded to properly control the second and third harmonics. The tuners are characterized for all frequency ranges, including harmonics, generating a list of hundreds of vector combinations for all impedances. The desired gamma is then achieved, finding the best vector combination offering the lowest error in magnitude and phase for fundamental, second, and third harmonics. The advantage of this solution is that it offers a broadband and simple-to-use setup for the end user. Another advantage is having multiple probes operating at the same frequency range also allows for higher tuning gamma compared to a single tuner, similar approach of a pre-match. The disadvantage of this approach is due to the fact that the tuners are separate, increases the insertion loss from the DUT and the reflective probe, reducing the overall final tuning range. A single multi-carriage tuner overcomes this limitation, integrating 2 to 3 tuners in one structure. As there are no extra connectors, the insertion loss is therefore reduced. The solution is also more compact and offering easier on-wafer integration. When selecting a tuner for your bench, there are some important considerations to keep in mind: speed, accuracy, and on-wafer integration. Speed. There's a high demand in design and validation applications for fast measurements. The test plan typically requires hundreds of measurements to cover all the conditions to test: multiple VSWR, frequencies, power, bands and signals, etc. Test plans can take many hours, and having an advantage on tuning speed of 30 to 40% compared to older tuner generations can definitely impact the productivity of your team. Accuracy. This is a key parameter that allows you to gain confidence in your measurements. How certain are you that when you move a tuner, it goes to the position you asked? Having an accuracy of 40 to 50 dB allows you to establish confidence that when you get a VSWR of 10 to 1 at a particular phase, you know that your tuner will be there. On-wafer measurements. As we mentioned earlier, adding components in front of the tuner reduces the tuning range at the DUT. This is particularly critical for an on-wafer application, as in order to connect the tuner to the DUT, you will need probes, couplers, and cables. Adding these components also creates a phenomenon called phase skew for modulated signal applications, where the impedance set by the tuner at a particular frequency will not preserve the same phase for the entire modulated bandwidth. We will be covering the tuning range and phase skew in the following slides. Tuning range. As we mentioned earlier, VSWR, or highest reachable gamma, is a critical parameter for the selection of a tuner. We typically refer to it as tuning range. It is important to understand the actual value at the DUT depends on what you have between the tuner and the DUT. The reflection signal will be in fact reduced by the insertion loss of the components. For on-wafer measurements, it's common to have a probe, cable, and coupler. Assume a tuner with a 15 to 1 VSWR specification equal to 0.87 gamma. A probe at 28 GHz is typically 0.4 dB, and assuming the best scenario, 0.6 dB between cable and coupler. This will only achieve 0.7 gamma at the DUT reference plane. This value will easily become lower if longer cables need to be used or if you go into higher frequency. We will discuss in the following slides what Mori has developed to support tuner range challenges. Phase skew. To explain phase skew, we will start by explaining how a tuner works at CW signal. We have a tuner and a cable connected to a DUT. A CW signal is used to stimulate the DUT, and the user wants to set a target gamma at the DUT as shown on the left side of the slide. The tuner and proper software loaded with proper Cascaded and tuner files will easily allow you to reach the target. But what does it mean to the tuner? What does a target gamma at the DUT mean to the actual tuner probe? To properly generate the target gamma, the tuner, which has already been characterized, will generate the X and Y positions to properly synthesize the calculated gamma
at the probe element reference plane, named reference A. The gamma at the reference plane will then be phase shifted to reference B, which is the connector reference plane. We will then cascade the S parameters of the cable used in the setup to properly get the desired target gamma. This process is all automated once the tuner is characterized at the proper reference plane. But what does it mean if we have a modulated signal? The tuner can only present the desired impedance at the selected frequency. Once a modulated signal is presented to the DUT, the transformation from DUT, reference B, and reference A of the tuner needs to be studied over the signal bandwidth of the signal, plus the adjacent channels need to be evaluated for ACPR. In fact, an impedance will also be set to the adjacent channels. For example, a 100 MHz signal plus two adjacent channels, low and high, equal 300 MHz. For simplicity, let's call the lowest frequency of this bandwidth Fmin and the highest Fmax. The target gamma at the DUT is the same as in the CW example. Therefore, the tuner will still set the same reference A impedance at the tuner element. We can assume for simplicity that at the probe element, the reference A gamma is the same for both Fmin, Fc, and Fmax. At reference B, the tuner connector, we will now have a phase variation of the gamma due to the distance between the probe element and connector. Reference A will now become reference B at Fc frequency, but the Fmin and Fmax frequency will see a different variation in phase than the calibrated Fc. We call this phenomenon phase skew. At gamma target, this difference will increase due to the increased physical distance between reference A and the target. In this case, Fmin and Fmax will see a further phase variation relative to the calibrated Fc. This phenomenon is independent from frequency Fc and only dependent on the distance between the target reference plane and the reflection element and the bandwidth of the signal. The end result means that with passive tuners, it's not possible to have a well-defined impedance pattern across the bandwidth of the signal. In summary, all tuners will see a variation of phase due to distance between the connector and probe element. This is typically 0.25 to 1 degree for megahertz depending on the tuner model. Adding cables, probes, and other components will increase this value and can go up to 1 to 2 degrees per megahertz. In this slide, we will show an example where 5 MHz WCDMA, 20 MHz LTE, and 100 MHz 5G signals are used. Phase skew of almost 300 degrees and more are easily achieved, not allowing for a proper validation of your device performance. What does this mean for your DUT? It means you select the impedance for max efficiency, but the actual impedance presented to your DUT has a 300 degrees phase difference across the bandwidth. In the next slides, we will be talking about the main challenges of FR1 and FR2 applications, which are in high demand now, and what Mori is offering to support customer needs. As I mentioned earlier, there are some important considerations for tuners: speed, ease of use, accuracy, and on-wafer integration. For FR1, there is less challenge due to the lower insertion loss of components at these frequencies. XT series tuners represent the next evolution in tuner technology for FR1. Faster, more accurate, and more repeatable. Updated mechanics and electronics results in a 40 to 100% faster mechanical movement, 50 to 85% faster tuner characterization, and 35 to 40% faster VSWR tests. The advanced speed is a mandatory need now in DVT applications. The software direct control is an easy way to integrate the tuner in your code, avoiding DLL import and speeding up connection speed and software implementation. Linear encoders on the horizontal axis ensure accurate carriage positioning and improved repeatability by 5 to 10 dB. The linear encoder allows for closed loop tuning, and once a position is set to the tuner has the ability to make sure that the position has been reached thanks to the feedback loop. The error at the target is a function of the difference between the target position and the actual position. This error is programmed to be -40 to -50 dB for XT tuners.
In this demo, we will show the simplicity of controlling the XT tuner using the web interface, as well as direct commands with one of the most popular high-level languages today, Python. In the demo, we'll use a set of 20:1 VSWR impedances for 360 degrees and validate against the VNA. Let's start by showing you the web interface shown here on the screen. This tool offers a simple way to check tuner operation and run quick measurements before I start integrating it into the custom software. Let's see some cool features. In the tuner control page, I can use this tool to control the tuner itself either by entering in a target value or simply by moving the target on the Smith chart. To do this, first I'll need to set up my tuner. I can easily load my tuner file as well as any front or back as parameter files if needed. Then I can go ahead and select my target frequency to control, and now I'm ready to move my tuner. Our tuner is going to start in our initialized position. Then I'll go ahead and select the value by moving the target on the Smith chart, select tune, and then verify this position against the VNA. And here I have a good match. Now let's take a look at the custom software integration using the Python script. Here I have my Python script loaded, and we'll go ahead and step through each of the commands and take a look at some of those results. First, I'll be communicating through the telnet library, and I'll first need to establish a connection through the Ethernet connection of my tuner. Let's step through this. So first, I've been able to successfully establish a connection with my tuner. Next, I'll be using the *idn command to query some information about my tuner. Here, it returns the model, serial number, and firmware version of my tuner. Next, I'll want to initialize my tuner in preparation for tuner control. That'll be done using the init command seen here on the left. Let's take a look. As you can see on the Smith chart, the X and Y positions of the motors on my tuner are going to go to a known starting position. Now that my tuner has been initialized, I'll need to load my tuner calibration. There are a few different ways to do this. First, I can do this using direct commands, as I'll be doing here. I can also copy and paste this into the FTP folder of the tuner itself, seen here, where I access it by entering in the IP address of the tuner. I can also store additional tuner files or S-parameter files if needed. Alternatively, I can also use the web interface loading section. Here, I'll be using the callib command to load the tuner file, and here's the tuner file name. Let's step through this. Now, I've also queried information about the calibration file that's been loaded. That's done using the calinfo. Here, I can see my tuner file model as well as number of frequencies that tuner file contains. Next, I'll want to load my tuner frequency. Here, this is done by using the frequency command and then selecting the frequency in gigahertz. I'll also be querying the frequency that's loaded by using the frequency command ? Let's step through these. Here on the left, I can see the two different tuner frequencies in my file, and I've loaded 2 gigahertz. Next, we'll be controlling the VSWR of 20:1. The software allows a few different ways to do this. I can either set up a gamma in terms of magnitude and phase, I can set up a VSWR starting point in mag and phase, or I can run a VSWR circle for max speed in either a step-by-step or a continuous mode. In this demo, we'll be using the third approach. Here, We will be setting a VSWR of 20 to 1 and then step 20 degrees at a time to complete the 360-degree rotation. This approach allows a user to take data with other instruments for each VSWR. Here, I'll first be initializing my VSWR with the VSWR init command and then selecting the magnitude that I want to set it to. Following this, I'll be stepping 20 degrees around the Smith chart, which will be about 19 steps. Let's take a look through this. Here we can see that my VSWR init set to a magnitude of 20, seen here with my marker. Then we're going to go ahead and rotate around the Smith chart in 20-degree steps. As we can see, I've also queried the gamma position for each VSWR step. The same circle can also be run in a continuous mode with no pauses in between the impedances. This speed can also be adjusted in order to synchronize with external instruments of interest, with 0.1 being the slowest and 1 being the fastest. Here, I'll be initializing my VSWR once again to a magnitude of 20, and then using the VSWR to do 360 and selecting a speed of 1, which is the fastest, I'll go ahead and sweep around my Smith chart. Let's take a look. As seen here, I've also taken a timestamp of how long it takes to complete each of these two different steps. As we can see, it took about 5 seconds to complete the step-by-step rotation and about 0.86 seconds to complete my continuous sweep.
Here, we take a look at the speed comparison between the XT generation tuners and our MT generation, with our XT generation tuners being the fastest at 5 seconds for 19 points and a continuous motion 0.86 seconds. At FR2 band, frequency and insertion loss become extremely critical, with challenges such as less tuning range, higher phase skew, and more complicated integration. Nano 5G is the latest design by Moray on how to support customers for 5G FR2 band. It covers 18 to 50 GHz with a 1.85 structure, allowing the signal up to 67 GHz to pass the tuner. This design allows users to reach the highest tuning range accuracy and ease of use thanks to the reduced size. Nano 5G is as big as an iPhone for reference, with a volume of 10 times smaller than previous tuner series. It's the ideal tuner for simple on-wafer integration with a light weight of 0.7 pounds without worrying about zoom interference, vibration, and usage of cables between the tuner and the DUT. It has an integrated coupler as an option for accurate vector receiver measurements and great position accuracy thanks to the X and Y encoders, with typical accuracy 50 dB. It also has direct commands for easy software integration. It's also important to mention the tuner is based on a 1.85 mm structure, allowing the second harmonic of 28 GHz to pass for proper measurements and eventually active tuning. In the next slides, we'll be talking more about tuning range and phase skew. Here, we have a 3D model of an on-wafer integration. In the picture, we have the Nano 5G tuner mounted on an RPP 305 positioner using a custom bracket. The tuner is then connected to the Nano 5G controller for external communication. Thanks to the small profile, Nano 5G, it enables easy on-wafer integration for several types of probe stations, such as form factor MPI. Typically, zoom interference could be a problem for direct probe mounting, but the Nano 5G has been designed with the objective for both larger and smaller scopes. Nano 5G allows for maximum tuning range. With a typical VSWR of 40 to 1, 0.95 gamma, at 28 GHz and 39 GHz, this tuner allows FR2 application on wafer. In fact, assuming a 0.4 dB insertion loss from the probe at 28 GHz, the user will be able to set up a minimum of 0.87 gamma at the probe tip. Another advantage is the option to include a coupler integrated in the tuner, still allowing for a gamma of 0.87. The coupler enables vector measurements between the DUT and the tuner. As mentioned, both tuning range and phase skew are a key improvement using the Nano 5G. Thanks to the direct connection, a minimum gamma of 0.87 is now achievable at the probe tip for 28 GHz and 39 GHz. The lack of cables allows for minimum phase skew. Using a signal of 100 MHz plus 2 left and right adjacent channels for a total of 300 MHz, the phase skew is only 30 MHz, where a previous generation of tuner and integration created more than 300 MHz phase variation. In summary, XT tuners offer faster and more accurate tuners on the market, from 0.225 to 26.5 GHz. MT tuners allow us to go up to 110 GHz on the waveguide structure, and the Nano 5G is the smallest and highest gamma tuner for FR2. We also offer manual tuners which offer a similar logic as our newest generation tuners without automation.